Hiya 13, so question 1, the ratio of the diameter of an atom to the diameter of its nucleus is. So this is just a fact recall. You were asked to remember the approximate order of magnitude for the atom and the nucleus, and then it's just substitution in, so you know the ratio is 10 to the minus 10 over 10 to the minus 15 gives you 10 to the 5, so that gets you C. In question 2, you are told that the kinetic energy of a body is determined from measurements of its momentum and its mass, and you're given the percentage uncertainties in momentum and mass. You find the percentage uncertainty in the kinetic energy by looking at the equation linking those two. So kinetic energy is momentum squared over 2m. I've derived that here, but you've got two lots of the percentage uncertainty in P plus the percentage uncertainty in M. The factor of 2 doesn't have an uncertainty associated with it. So you've got two lots of 3% plus 4 for the M value. So you've got 10% there. In question 3, a car travels clockwise around a circular track of radius r. What is the magnitude of the displacement from x to y? I've drawn that on. And you'll then see that you have a right-angled triangle where you know the opposite and the adjacent, and then it's just Pythagoras. So you've got a squared plus b squared equals c squared, where a and b are both r. So r squared plus r squared must equal your displacement squared. Gives you the displacement of the square root of r squared plus r squared, which is 2r squared. The r squared comes out and you've got r, but root 2 remains as root 2, giving you C. In question 4, a little trickier, a stone of mass m is projected vertically upwards with a speed u from the top of a cliff. The speed of the stone when it is just about to hit the ground is v. Momentum is a vector, so direction matters when you're looking at the change in momentum. So you know initially it's moving up, so we'll consider that to be positive. And then finally it moves down, must have negative velocity. So the initial momentum is mu, the final momentum is minus mv. So the change in momentum is the final minus the initial. So you've got minus mv minus mu, which is going to give you, if you just look at my working, minus mv minus mu minus m brackets v plus u. But because it asks for the magnitude, it's asking for the absolute value of it. So it's mv plus u. In question 5, a car accelerates uniformly. The car passes point x at time t1 with velocity v1 and point y at time t2 with velocity v2. The distance xy is s. The following expressions are proposed for acceleration, which are correct. So take your CVAT equations and substitute in basically to check which ones are right. So we know that v squared equals u squared plus 2as. You can rearrange that and it's v squared minus u squared over 2s. V is the final velocity, so that's v2 squared. U is the initial, so that's v1. So we can see that expression 2 is correct, so that's fine. V equals u plus at rearranges to v take u over t. V, the final velocity, is v2. U is the initial, is v1. And then delta t is t2 take t1. So we can see that expression 3 is also valid. The third CVAT equation we can use is s is ut plus a half at squared. When you rearrange that, you get to 2s minus ut over t squared. You can see then that expression 1 is wrong. There needs to be a factor of ut on the numerator, and there isn't, so it's 2 and 3 only. In question 6, a ball is attached to a string and it's made to rotate with a constant speed along a horizontal circle. The string is attached to the ceiling and makes an angle of theta with the vertical. The tension in the string is T. So you can see I've immediately sketched this out, and then I have expressed in terms of horizontal and vertical. So we've got horizontally, we've got T sine theta, and vertically we've got T cos theta. We know that if something is moving in a circle, the net force is towards the centre of the circle for the centripetal force. What is correct about the horizontal component and vertical component of the net force on the ball? So we know that if it's moving horizontally, there cannot be a resultant force vertically. So we know that up has to equal down. Now we know that down we've got the weight, which is mg, and so mg must equal t cos theta to cancel out. So that means that you have 0 for your vertical component, so C or D. And then horizontally, we know that we've got t sine theta just from the diagram and resolving our vectors. In question 7, a person lifts a total mass of 20 kilograms. Now it's paper 1, non-calculator. We take G to be 10, so we've got a weight of 200 newtons moving through a vertical distance of 0.6 meters. The person repeats the lift n times to transfer a total energy of 6 times 10 to the 4 joules. What is the value of n? So work done, we know as force times distance in the direction of the force. So we've got 200 newtons lifted through a vertical distance of 0.6 meters. So one lift is worth 120 joules. We know that the total energy transferred was 6 times 10 to the 4. So we need to divide that by 120 for the one lift to find out how many lifts in total we have. And then it's just maths. You should end up with 500. So you can pause and have a look there if you got that wrong. Question 8 was a bit trickier. 3 samples of the same liquid are mixed in an insulated container. The masses and initial temperatures of the sample are given in the table. The same liquid means that the C value is the same for all. We know that sample 1 is held at the highest temperature, and so it will give energy to sample 2 and 3, which are at the lower temperatures. So the Q lost by sample 1 in total has to be equal to the Q gained by sample 2 and 3. We know that that value is equal to Q is equal to mc delta T for the Q lost by sample 1. So for sample 1, the mass was 2m, C is the fixed value, the specific heat capacity. We know that once equilibrium temperature is reached, we'll call that TF for T final. The temperature change for sample 1 is going to be 60 that it started with minus the final temperature, which we know will be lower. We know that all of that energy, which is Q here, has to equal the Q gained by sample 2 and 3. So sample 2 also had a mass of 2m, same specific heat capacity value, but this time its temperature change, it will increase in temperature. So to find the temperature difference, we'll do the final temperature minus the initial, so TF minus 30. And then the sample 3 only had a mass of m, C again, and then again it will raise temperature because it's gaining energy, so therefore TF minus 0 to find its temperature change. You can see that you've got m and c as factors in each part of the equation, so I'm just going to cancel those. So I am then just going to solve algebraically, so you can follow me round down, and you'll get to 36 degrees Celsius there. So just pause and have a look. In question 9, a balloon of volume V contains 10 milligrams of an ideal gas at a pressure P. An additional mass of the gas is added without changing the temperature of the balloon. This change causes the volume to increase to 2V and the pressure to increase to 3P. What is the mass of the gas that was added to the balloon? So not the final mass, but the mass that you had to add. Now, we know that if the temperature does not change, PV is constant. Okay, so initially we had PV, and finally we had 2V multiplied by 3P, because the volume doubled and the pressure increased to 3 times that. So we know that actually what has happened is we must now have 6 times the mass in order for that to occur. That's the only way that you're going to get 6 times the value of PV. Okay, if you didn't change the mass, PV would be constant. So in order to get a value that's 6 times larger, we know that we have to have total mass being 6 times larger. So we know then that the mass added must mean that the final value is 60 milligrams, because we had 10 to begin with. 6 times larger than that is 60. 10 already existed, so it must be that we added 50 to this. In question 10, an object oscillates at the free end of a vertical spring. That's your first clue that springs follow simple harmonic motion. So we know that this ratio stands and holds true. Acceleration is proportional to the negative of the displacement. A is proportional to minus x. The graph shows the variation of the object's position, which is x, with time. At which position does the object have zero velocity and negative acceleration? Okay, well, firstly, the gradient of a position against time graph is velocity. So we need the gradient to be zero. So we're looking where the gradient is horizontal, which is either A or C, not B or D. And then we know that A is proportional to minus x. So if the position is positive, then A will be negative, which is what we're looking for. So this is why we choose A and not C. In question 11, a sound wave travels through a gas at a speed of 270 meters per second. The graph shows the variation of the displacement of the gas with distance d from the source. What is the frequency of the wave? So you can see from the diagram that the wavelength is 1.5 meters. Always check your units there. We can also see from the question that v, the velocity of the wave, was 270 meters per second. Frequency is wave speed over wavelength. That's something you should remember. And then it's just a case of 270 divided by 1.5. You don't have a calculator, so I'd put it into fraction form. 270 over 3 over 2 is 270 times 2 over 3. Gets you 180 hertz there. Question 12, I think, was one of the trickier questions on the paper. A point source emits a sound wave of amplitude z. A person stands a distance L from the source. The amplitude is changed to 2z, so the amplitude doubles. What distance must the person move through? So that means I'm already at a position. How much further do I have to go in order to hear the original intensity again? So we know that intensity is proportional to amplitude squared. So we know that if the amplitude doubles, which we're told in the question it does, it goes from z to 2z, then a squared is increasing by a factor of 4. I also know that intensity is proportional to 1 over the position squared, 1 over x squared. So decreases with distance away from the source. So I have two statements of proportionality for intensity. I is proportional to a squared. I is also proportional to 1 over x squared, which means that those two things are proportional to each other. A squared is proportional to 1 over x squared. Now, A doubled, so the intensity increased by a factor of 4. That's what happened to begin with. But then the question says, what do I have to move through to go back to hearing the original I value? So if the intensity factor increased by 4, then I know that I need to move to a distance that is then going to reduce the intensity by a factor of 4. Okay, so I know that 1 over x squared needs to be times a quarter. Okay, so if 1 over x squared needs to be multiplied by 1 over 4, then x squared must be 4 times larger. Okay, which means that x must be root 4 times larger, so it must be 2 times larger. Okay, so I know that my position now needs to be 2L compared to the original point. Okay, that's not your final answer though, because that's from your origin of your source. It asks you what distance must you move through. You are already at L. To get to 2L, I only have to move through L, and so that gets me answer A. In question 13, unpolarized light with an intensity of 320 watts per meter squared goes through a polarizer and an analyzer, originally aligned parallel. So, to begin with, I have 320 watts per meter squared. The first thing to remember is that if you have unpolarized light, the polarizing filter will always reduce this intensity by 50%. And so only 160 watts per meter squared is going to reach the analyzer. The analyzer is then rotated through 30 degrees. And they give you a trig expression, a trig identity, that cos 30 is root 3 over 2. What is the intensity of the light emerging from the analyzer? Well, we know that the intensity of light compared to the original value before it passes through the analyzer is given by I is equal to I naught cos squared theta. That's in your data booklet. Theta is the angle of the analyzer filter relative to the polarized light, so that's 30. So I know that the original incoming intensity on the analyzer was 160. We worked that out in the first step, and I'm just multiplying that by √3/2 squared. And then it's just simple substitution in. So the key thing is that you remember that you have to reduce by 50% before you plug in. In question 14, you have 4 particles, 2 of charge plus Q, 2 of charge minus Q. They are positioned on the x-axis as shown. A particle P with positive charge is placed on the y-axis. What is the direction of the net electrostatic force on this particle, so overall? So we know that particle P is equidistant between negative charges, minus Q and minus Q on this side, and plus Q and plus Q on this side. So I've drawn out the field from a positive and a negative on the respective sides they're on so that you can see what that looks like. So if you are point P here, you are subject to the positive field and the negative field. So we know that we've got field lines pointing away from the positive plus Q and coming in towards the minus Q. Okay. Now, I just want you to look at this section and this section. You're equally far from these 2 points, and so you at this position you're going to have these two cancelling. Okay, same here. The vertical component of this points down. The vertical component of this bit points up. So the vertical components are going to cancel because you're equally far from both. But the horizontal components of both are to the left, both of them, and so they add rather than take away. And so you know that overall you're going to have a force felt to the left, and that gets you D. In question 15, a battery of negligible internal resistance is connected to a lamp. A second identical lamp is added in series. What is the change in potential difference across the first lamp? And what is the change in the output power of the battery? Just see that just a little bit further. So I've drawn it out. We've got one bulb, and then we keep the same power supply, but we now have 2 bulbs. We know that in series voltage is split, and so that we know that the voltage across lamp 1 is going to decrease. It's actually going to half. And then we know equations that will help us for the output of the power. So current is voltage divided by resistance, and power is equal to current multiplied by voltage, or I squared R. So from equation 1, we should see that the total current flowing through the circuit is going to be reduced, because while the voltage supply hasn't changed, the total resistance of the circuit has increased. Okay, and so if R has got larger, I has got smaller. So we know that current is reduced. So from equation 2, we should see that while V total drawn from the supply is the same, if the current in the circuit has dropped, the power output of the circuit also must drop. Okay, so that should be A. Okay, question 16. I always redraw these circuits when they're in diamond form because I don't visualize them very well while they look like this, but you might be able to. A circuit consists of a cell of EMF E is 3 volts and 4 resistors connected as shown. Resistors R1 and R4 are 1 ohm, and resistors R2 and R3 are 2 ohms. What is the voltmeter reading from these 2 points? So I've redrawn, let me see if I can show you both at once, because you're just tracing loops that you can take. So from the power supply, you can go through R1 and R3 and come back round, or you can go through R2 and R4 and back round. So I've drawn it in the way that I'm more familiar with. So you can either go through, and if you look, you can see which one I'm talking about here. R1 is worth 1 ohm, R3 is worth 2, and then I come back round. Or I go through R2, which is worth 2, and then R4, which is worth 1, and then back round. Okay, I know the EMF is 3 volts. The voltmeter is reading in between R1 and R2, so that's here, and in R1 and R3, sorry, so that's here, and then R2 and R4, so position between the two. So I know that if I am a charge, I have 3 volts at this point. Before I've gone through any components, I'm still at a potential value of 3 volts. I know that by the time I have passed through both resistors, I will have a potential of 0 volts. So I know that 3 volts has to be transferred across my pathway. I know that I've got a 1 ohm resistor and a 2 ohm resistor, so it's going to take a 1 out of 3 share of 3 and a 2 out of 3 share of 3 volts. So I'll drop 1 volt across the 1 ohm resistor and 2 volts across the 2 ohm resistor. So if I'm at a value of 3 volts here and I transfer 1, at this point I'm at a potential value of 2 volts. If I take the second path though, I'm at 3, I transfer 2, at this point my potential value is 1 volt. Okay, so I've listed this below. So you can see at this point I had 3 minus 1, I have 2 volts of potential. Here I have 3 minus 2, I have 1 volt of potential. A voltmeter reads potential difference. It's saying what's the difference in potential from this point to this point? Well, the difference is 2 to 1. It's 1 volt difference. So that gets you answer B. In question 17, the coil of a direct current electric motor is turning with a period t. At t equals 0, the coil is in the position shown in the diagram. Assume the magnetic field is uniform across the coil. Okay, so I've labelled on current flow. I know that it's a DC motor, so the current flow stays the same. But when the coil flips, the relative direction of the current to the field is going to change. So every half turn, the current direction on this side is going to flip. So it changes direction twice in one complete turn. Now, from my left-hand rule, I know that force, field and current are at right angles to each other. If my current changes direction and flips, then my force also changes direction. And so that I know that within one turn, I'm going to have a force direction change twice. Okay? Direction is shown by positive and negative. So I have positive force direction. It changes, so that's change 1 after flip halfway around the coil. Sometime later, it changes from negative to positive again. That's change number 2. And so the answer is A. In question 18, a satellite is orbiting Earth in a circular path, which means there must be a centripetal force, at constant speed. 3 statements about the resultant force on the satellite are given. Which combination of statements is correct? Well, if we have a circular path, there must be a centripetal force. We know that the centripetal force in this case will be provided by the weight of the satellite. So the statements are, the force is equal to the gravitational force of attraction on the satellite. That's true. Gravitational force of attraction is weight. 1 is true. It is equal to the mass of the satellite multiplied by its acceleration. Weight is mg, g is acceleration due to gravity. 2 is correct. It is equal to the centripetal force on the satellite. Absolutely, because that's the force that is acting towards the centre of the circle that the satellite is moving in. And so D is correct there. In 19, the gravitational field strength at the surface of the Earth is often taken to be 9.8 newtons per kilogram. The use of this value to calculate the weight of an object above the surface of the Earth is, and then you need to pick the correct answer. A paradigm shift in our understanding of gravity? No, that's not true. That's just one to know. It wasn't a change in our idea. It's not an attempt to model gravitational fields. We found these values empirically. C, it was not an outcome from a peer review. it was an outcome of a thought experiment that Newton had. D, an approximation used for estimation purposes. Yes, absolutely. We are using 9.8 newtons per kilogram, but we've seen with Firefox that even around a classroom, it does fluctuate ever so slightly. It does vary with distance, but at heights close to the Earth, the difference is negligible, so we can take it to be an approximation. So D is true. In 20, a student measures the count rate of a radioactive sample with time in a laboratory. The background count in the laboratory is 30 counts per second. Okay, what is the time at which the student measures a count rate of 45 counts per second? So, we can immediately get rid of the background count so that we have the source count. So we can see 150 goes to 120 because the background is 30, and 90 goes to 60. So you can hopefully see that 120 dropped to 60 in 20 seconds. That value has halved, which tells us that the half-life is 20 seconds. What is the time at which the student measures a count rate of 45 counts per second? Well, let's have a little look. The source itself will decay each half-life. It will go from 120 to 60 in one half-life, 60 to 30 in two half-lives, and 30 to 15 in three half-lives. But the 15 is purely from the source. The measured rate will also include the background. So 15 plus 30 gets you the 45 that you would be reading. So it will take you three half-lives. We've seen that a half-life is 20 seconds, so therefore it is a 60 seconds half-life. In question 21, 3 statements about the binding energy are provided. 1, the binding energy is the energy required to completely, i.e. to infinity, separate the nucleons. This is true. The binding energy is equivalent in units of energy to the mass defect when a nucleus is formed from its nucleons. Also true. The binding energy is the energy released when a nucleus is formed from its nucleons. Yes, we know that it's in its lowest energy state when it's a nucleus. You have to put energy in to pull them apart. So yes, energy must have been released when the nucleus was formed, giving us D. In 22, let's see if I can squeeze this all in. The diagram shows atomic transitions E1, E2 and E3 when a particular atom changes its energy state. The wavelengths of the photons that correspond to these transitions are lambda 1, lambda 2 and lambda 3. So we know by definition that the energy of a photon is given by hc over lambda. H and C are constants, so E is proportional to 1 over lambda. We can look at the transitions and we see that the energy difference E1 is largest, E2 is the middle value, and E3 is the smallest energy transition. We know that if E is proportional to 1 over lambda, then the largest energy difference will correspond to the smallest wavelength required for that, and vice versa. So it goes E1, E2, E3 for largest to smallest, which means lambda 1, 2 to 3 goes smallest to largest, which means that lambda 3 is bigger than lambda 2, is bigger than lambda 1. We also notice that E1 transition, the energy difference, is equal to E3 plus E2. The same energy transition has to happen. That means that hc over lambda 1 equals hc over lambda 2 plus hc over lambda 3, meaning that we can mathematically say that D is correct. In 23, carbon 12 and hydrogen 1 undergo nuclear fusion to form nitrogen. What is the number of neutrons and the number of nucleons in the nitrogen nuclide? So we can see firstly, a photon is a 0, 0. We know that before and after we have to have numbers conserved. So 12 plus 1 is 13, 6 plus 1 is 7. So we can see that the proton number is 7, the nucleon number is 13, but it doesn't ask for the proton number, it asks for the neutron number, so we need to find the difference between the two, giving us 6 and 13. In 24, it says 2 sets of data shown below with circles and squares are obtained in 2 experiments. The size of the error bars is the same for all points. What is correct about the absolute uncertainty and the fractional uncertainty of the y-intercept of the two lines of best fit. Okay, so let's remind ourselves, fractional uncertainty is the absolute uncertainty divided by the value. If the absolute uncertainty is the same for both circles and squares, which hopefully you can see it is, so the length of the error bar is the same for both, it means that the absolute uncertainty is the same for both, but you can hopefully see that the circle values are larger than the square values. So it makes sense that the fractional uncertainty is going to be larger for squares because your absolute uncertainty is now over a smaller number for squares. So fractional uncertainty is larger for squares, and this allows us to pick the right answer. So we know that the absolute uncertainty is the same because the error bars are the same, but that's going to lead to a bigger fractional uncertainty for the squares. Okay, 25, this was a tricky question. An ambulance emitting a sound of frequency f is moving to a point x at a velocity of 40 meters per second. A car is moving away from x at a velocity of 20 meters per second. So the values are relative to this position. We can see then that the ambulance is moving towards x 20 meters per second faster than the car is moving away. So the relative velocity between the ambulance and the car is 20 and 0. Okay, so in each second, the ambulance is going to get 20 meters closer to the car. The speed of sound is v. What is the frequency detected in the car? So now we have our relative values between a moving source and a stationary observer because we're looking at relative velocity. So from the perspective of the car being still, the ambulance is moving at 20 meters per second. We take our moving source equation from our data booklet, f dash is f v over v plus or minus u of the source. We then use our common sense and we know that if the moving source is coming towards us, the wavefronts are going to get squished up, the frequency is going to increase. So for the frequency f dash to be larger than the frequency in reality emitted, we know we need to choose the negative sign so that this whole value is bigger than 1. So we take this form, and then us is u of the moving source relative to the stationary observer, and that's 20. So we are looking for f v over v minus 20, and mathematically you can see that that is equivalent to A. In 26, a telescope can just resolve images that are separated by an angle of 2 times 10 to the minus 7 radians. Two stars are a distance of 4 times 10 to the 16 meters from each other. What is the maximum distance between the stars and the telescope for their images to be resolved by the telescope? So this is small angle approximation. So we've got our two stars, and that separation is capital D. That is then at a distance lowercase d to the telescope. So the telescope is over here. You've got your angle of separation. So we're doing small angle approximation where we say tan theta is big D over little d, but that's approximately equal to theta, and it's substitution in, which gets us to our final value. So you can pause and just have a look at the maths there. But you have to remember that because little d is so much larger than big D, we can take our small angle approximation. In 27, this was a tricky one. A ray of white light is normally incident on a thin layer of oil on water. The refractive index of oil is 3 over 2, and the refractive index of water is 4 over 3. So I've listed that in decimal value just because it helps me to visualize which one's largest. So we've got air, n is 1, to oil, n is 1.5, to n water is 1.33 recurring. Now, we know that reflection at a boundary occurs, but that phase change during that reflection will only happen if light reaches a boundary of a higher refractive index. So if light is incident on the oil from air, any reflection will have a phase change. But any white light that reaches through the oil and then reflects off the water boundary at the bottom, there will be no phase change during that reflection. So we've got reflection at the first boundary, but no reflection at the second. The wavelength of violet light in air is lambda V. What is the minimum thickness of the thin layer of oil so that the colour of the reflected light is violet? Okay, in order to see the violet light, we need constructive interference with the violet light that is reflected at the first surface and reflected from the second surface. If it's destructive, it's going to cancel out and we won't see it anymore. Now, we know that violet light will undergo a lambda over 2 path difference change during the air-oil reflection because there is a phase change. So the path difference is half a wavelength. We know that that does not occur, and so we need to introduce it at the oil-water boundary so that when they re-add later, they're back in phase again. So we have to introduce a path length change of 1/2 lambda within the oil so that basically the oil has to travel an extra half a wavelength in terms of number of full wavelengths plus half a wavelength so that it's returning to the point where the first reflection happened in phase and can constructively interfere with the violet light that reflects off the first boundary. That's important. So then, coming down here, our constructive interference expression is 2dn is 1/2 lambda. I can rearrange this to find my distance, because d is my optical distance. My path length I need is 1/2 lambda. So d, rearranged, is lambda over 4n. Now, this n is the refractive index of the oil, which was 1.5. And so I know that my optical distance needs to be lambda over 4 lots of 1.5. And that gets me lambda over 6, which gets me answer A. For 28, a beam of light containing 2 different wavelengths is incident on a diffraction grating. The wavelengths are just resolved in the 3rd order of diffraction. What change increases the resolution of the image? Okay, so we have a resolvence factor is lambda over delta lambda is equal to mn. Now, we can clearly see that if we increase the number of slits illuminated, n, we increase the resolvence factor, so we'll increase the resolution of the image. So we want to increase capital N. Therefore, we want to illuminate more slits. So if we increase the width of the incident beam coming into the diffraction grating, we will be illuminating more slits, N will get bigger, thus R will get bigger, we will have more resolution available. So the answer is A. In 29, 2 satellites are in circular orbits around the Earth. Both satellites have the same mass, and satellite X is closer to Earth than satellite Y. What is correct for the orbital periods of X and Y, and then the total energies of X and Y? So we should see, firstly, easily we can negate A and B. So we should see that X is closer to Earth, and so its orbital period is going to be shorter. So that gets us C or D. For total energy, I've popped it down here because I couldn't fit it on the question. Total energy of the satellite is the sum of its kinetic and potential energy, which is a half mv squared for the orbital velocity, plus the potential energy, which is minus gmm over r. I have expressed my orbital velocity in terms of gm over r square rooted, but because I've got orbital velocity squared, I get gm over r. This is from your data booklet, so this section gives me gm over r. That expression is in your data booklet. So then it's just algebra. So I can see my total energy of an object in orbit is equal to minus gmm over 2r. And this expression, if I pop it up here, is my total energy, so that's my second column that I'm looking for, we can see that the value is going to be greater for y than it is for x. My YR value is larger than my XR value. So if my Y value of R is larger, this whole value is smaller, but it's a smaller negative number, which on a number scale is a larger absolute value. So you get D. In question 30, this was a nice easy one. An electric field is established between two electrodes separated by distance d, held at a potential difference of V. A charged particle in this field experiences a force F. What is the charge on the particle? Well, electric field strength is the force per unit charge, but it's also the voltage per unit distance across the two plates. You're just rearranging for Q and choosing the right one. 31 relies on a similar idea to question 29. A satellite of mass m orbits a planet of mass m, big M, in a circular orbit of radius r. What is the work done that must be done on the satellite to increase its orbital radius to 2r? So we know that the total energy of a satellite at a given position is equal to minus gmm over 2r. Now, if r doubles, then the total energy is now equivalent to minus gmm over 2 lots of 2r. I can find the difference from my final and my initial energy from when I'm at r to 2r, and that allows me to find the work done. So you can see that what I've done is I've expressed my total energy in terms of 4r, just for simplicity for the maths. So I know that my total energy at any point is minus gmm over 2r, which I can express as minus 2 gmm over 4r. They're mathematically equivalent. The reason I've done that is because when I increase my radius by a factor of 2, I know my total energy is now going to be minus gmm over 4r, so I can now compare with like terms. So my final is minus gmm over 4r. My initial was minus 2 gmm over 4r. Minus minus is a plus. So therefore, my work done is gmm over 4r. In question 32, the diagram shows equipotential lines for an electric field. Which arrow represents the acceleration of an electron at point P? So we're at a position of higher potential here and lower potential here. So this is your positive side, as this is your negative side. We know that an electron is going to be accelerated towards a higher potential value. So we'll move towards the left. In question 33, a student states 3 facts about the time constant tau of an RC series circuit, a resistor capacitor series circuit. So I've sketched that out here. So you've got your power supply, it can charge your capacitor. You've got your resistor here. So you have to decide which are correct. Now, we know that it follows an exponential change, so in terms of the shape of the graph. So we know we have these expressions. V is V naught e to the minus t over tau. So this is for the discharge of a capacitor. So if V naught is your maximum value, then when t is equal to tau, your e to the minus t over tau is equal to e to the minus 1, which is 0.37. So your voltage compared to your original voltage when t is equal to tau is 37% of the initial value during discharge. So time required for the capacitor to be charged through the resistor to a voltage of 0.632 volts from an initial value is correct, because this is charging, not discharging. And it works in reverse, right? So if by time t, if the capacitor is initially fully charged, it will have discharged to 37%. That is the same as in reverse, it will charge up to 0.632 volts. right? So think about it. You've got a discharge-charge relationship. So if it is that the capacitor is charging, then initially the resistor takes the biggest voltage value, but as the capacitor value increases, the resistor voltage is dropping, and then it's the same vice versa. But the total voltage always has to add up to the voltage from the supply. So 1 is correct. 2, it is the time required for the capacitor to be discharged to a voltage of 0.632 volts. No, that's incorrect. We just proved mathematically that that's 0.37 volts. 0.37 of the original voltage. And then 3, it is the product of the resistance of the resistor and the capacitance, RC. Yes, that's just one that you needed to remember. Tau is equal to RC. So that gets you B. 1 and 3 are correct, but 2 is not. In 34, what is the purpose of using a step-up transformer at a power station? This is really just a basic recall. It's to increase the voltage so that the current is lower for the same power transmission, which will decrease energy losses through the power lines. In 35, it was a bit more difficult. So 2 coils of wire are wound around an iron cylinder. 1 coil is connected in a circuit with a cell and a switch that is initially closed. The other coil is connected to an ammeter. The switch is opened at time t0. Okay, so before the switch is on, there's nothing going on, full stop. But when you close the switch, all of a sudden the current in circuit 1 rapidly increases from 0 to whatever the current value of the circuit will be. So we do have a rapid increase in current at t is t0, and it very quickly stabilizes and becomes a standard value. But during the rapid increase in current, it produces a changing field. So we have a changing magnetic field inside of coil 1, which cuts through coil 2, which induces an EMF in the second coil, so we do get a current flow. But as soon as you've got a consistent DC current value in the first circuit, there's no changing field cutting anymore because it's a constant magnetic field. So after that point, there won't be an EMF induced. So before T0, there's nothing because there's no current flowing in circuit 1 at all, so there's no magnetic field. Nothing can be shown on the ammeter. But then we very quickly see a peak of current during the initial transition from 0 to maximum current in circuit 1, causing a changing field cutting through 2, but that quickly drops back to 0 again once the current here becomes constant. In 36, a student quotes 3 equations related to atomic and nuclear physics. Which equations refer to the Bohr model for hydrogen? Okay, well, quick giveaway, the second equation is clearly a radioactivity equation, so no, that is not for the Bohr model. But both 1 and 3 are equations that we looked at when we learned about the Bohr model for hydrogen. So we've got the first one is the energy level of electrons, depending on their shell number. And then the third one is the quantized angular momentum of the electron, which is the first postulate of the quantum model, which is the Bohr atom, so B. In 37, let's see if I can fit the whole thing in, maybe not. Monochromatic, so 1 wavelength, electromagnetic radiation ejects photoelectrons from a metal surface. The minimum frequency for which this is possible is F, so this is the threshold frequency, is F. When radiation of frequency 2F is incident on the surface, the kinetic energy of the photoelectrons is K. What is the kinetic energy of the photoelectrons when the frequency of the radiation is 4F? Okay, so the energy of the photon is equal to HF, which is equal to the sum of the work function of the metal and the kinetic energy of the electrons leaving the surface. We know that when we have frequency F, we have our threshold frequency, which means that we have enough energy to meet the work function, and so the photoelectric effect does happen, but there's no extra energy left for the electrons in terms of kinetic energy. So the electrons leave the surface, but with 0 joules of kinetic energy. So all energy is transferred to the work function. So I can say that the work function is equal to hf. When the frequency is doubled to 2f, the energy of the photons will therefore be 2hf, which will still be equal to the work function plus the kinetic energy of the electrons. So 2hf is equal to the work function, which we already proved is equal to hf, plus the kinetic energy. You can hopefully see mathematically that K must also equal hf, so the kinetic energy value is hf. That then helps us in our final step. So when f is quadrupled, so when the frequency of the incoming photon is 4 times the original value, the photon energy is 4hf, and that energy is transferred to the work function plus the kinetic energy. So the work function is hf. The energy of the photon is 4hf, leaving the kinetic energy that is available for the electrons to be 3hf. This is now 3 times the value of the kinetic energy that it was originally, and so it's 3k. And that gets us C. Last page, 38. A beam of electrons moving in the direction shown is incident on a rectangular slit of width d. So we've got an electron beam coming from left to right. We've got a slit with width d. So we know that delta x, which is our uncertainty in our position, must be equal to d. It's the uncertainty in the start position of the electrons along the y-axis, because we don't know where it's going to start from this slit. So the component of the momentum of the electrons in direction y after passing through the slit is p. The uncertainty in p is, and then you choose which one. So we take Heisenberg's uncertainty principle, delta x delta p is greater or equal to h over 4 pi. Rearrange for uncertainty and momentum, so delta p, because that's what we're looking for, is equal to h over 4 pi delta x. But we know in this scenario that our uncertainty in where it started from as it moves off in the y direction is equal to the width of the slit, and so delta x becomes d, which means that delta p, the uncertainty and the momentum, is inversely proportional to d, so you get answer B. In 39, the Rutherford-Geiger-Marsden experiment shows that, and then you just need to remember this is your alpha particle scattering experiment. We know that they do obey Coulomb's law. They're electrically charged, they will do. There is a fixed nuclear radius for each nucleus is not true. It doesn't show that at all. That's a next step. And we also know that different nuclei have different elements, have different radius values. But we do know from the experiment that a very large proportion of the alpha particles travel straight through the gold foil and are undeflected. So that is C. And then last but not least, a photon has a wavelength lambda. What are the energy values and the momentum values of the photon? So the de Broglie wavelength is equal to h over p, so h over the momentum, which is h over mv. So we can say that the momentum of a photon is given by h over lambda from rearranging. So that gets us A or C, and then we know the energy of a photon expression. We should know that by heart, really. Is equal to hc over lambda, because E equals hf, and that gets us answer A.